This is our nuclear decay lab. You can see we have our three sources here. Our polonium-210 source is our alpha particle source, and then our thallium-204 is our beta particle source, and then our cobalt-60 is our gamma particle source. And this thing making the noise is our radiation monitor, and it's attached to our LabQuest, and you can see that each time you hear that sound, there is a particle that's coming off, most likely from, most of them are going to be coming from the source here, but there's also background radiation that is coming in. We're going to figure that out too. Over here are this is just thin aluminum foil. These are absorbers. We're going to put these over the samples to see how they absorb the radiation, the different kinds. And then this is a thicker version of the just thin metal. And then we got this is a actually fairly thick piece of aluminum. And then here is lead, very thick, heavy. Okay, and then we have our isotope generator. That's going to be for our barium 137 we're going to be studying as in a half-life. Okay, so those are the components, and this is a timer. And so this is going to be what we'll be using for the lab. So we want to determine what the background radiation is, and that's the radiation that's coming from the ground, from space, coming from objects in the room. But there's an average background radiation that if we do this for 3 minutes and then divide by 3, we'll figure out the counts per minute, which are pretty steady. I moved all the sources, radioactive sources away, so we don't have to worry about those. So what I'm going to do is, make this new. I should start again, and then press the timer, and then we'll let this go for 3 minutes. I'm not going to show the whole thing, but we'll just let it go until we get a couple of counts. So you can see it's going to be adding up. Not a lot, thankfully. We don't want a lot of background radiation. But let's find out what the average is. Okay, we're closing in on 180 seconds, or 3 minutes. And this timer gives everything in seconds. You can see that as we're coming up on it here, we're 36 counts. But whatever it is, when we hit 180 seconds, that's what we're going to take to be the counts for 3 minutes, and then we'll divide by 3. So when we hit that 3-minute mark, instead of shutting off the timer, I shut off the phone. So, but I was really happy that it was at 42, because then that's easy to divide by 3. But there's the background radiation. Counts for 3 minutes were 42. All right, now normally this one is where students, this part will be in the lab where the students count or measure the counts of these different sources over the course of minutes. But I'm just going to show you, I'll just give some examples here. So here's our polonium-210, and this is our alpha source. These are the largest of the subatomic particles that we have for this lab. And you can see inside there, that's the sample. And the radiation will come out this side too, but there is something in the way, so usually flip it up like this. And you can see the counts going, so there's definitely a lot of activity there. So this is 0.7 mil, or 0.7 thousandths of an inch of aluminum, and you can see it's really thin. If we put that over top, I'm just going to sit right on the sample, and not worried about the counts exactly. Just listen to the clicks. You can see that that's reduced it quite a bit. It goes back up, and then this is our plastic. I think this is 0.03 or 3/100ths of an inch plastic. Put that on. And the counts drop dramatically. A little bit higher than background radiation, but this is really taking care of it. Because of that, the alpha particles are just helium nuclei, and those are those are pretty big. So make sure that this, yeah. And so and when you have something that's dense like this in the way, it tends to deflect and absorb them, the alpha particles. Here is aluminum, and it is it's 0.025 inches, so about the same thickness as this. You can see that the count is pretty low. It's probably close to background radiation. And then we'll put in, it comes back, and then we'll put in the lead. If I can fit it under here. Yeah, nothing. And that lead, the lead, it's 1/4 of an inch for the thickness. So what we're hearing is most likely background radiation. Okay. Let's do this for, all right, so that's for the alpha particle radiation. And again, just to show you what you need to block this kind of radiation. And for alpha particles, you don't really need much, even a just thin piece of plastic can block quite a bit of the alpha radiation. Okay, here's the thallium-204. We're going to do the same thing that we did for the alpha source. So this is our beta source. I'm going to put it here. Now this is a fresh source. You can see it's going crazy. So this will give us an even better idea what's going on here. And you can, of course, shut off the sound if you want to on here, but I'm going to leave it. Let's put a shield over here, something to absorb. And you can see that it doesn't do very much. And then we'll put on the plastic. It's starting to hurt my ears. There we go. Definitely has an effect. And then here's the aluminum. So I'm using the same ones as before. So a little bit above background radiation. And then let's see what the lead does. Shouldn't be surprised if lead cancels it completely out. Yeah. You can see in that short time the number of counts, so that's really pretty high activity for the beta source. So in case you're wondering if I'm going to survive the lab with all those counts, man, that's really a high level of radiation. Here's the same sample, and here's the counter. It's 10 centimeters away. And look what it's doing now. The reason I had it so close was because a lot of our samples are older, and most of the radioactive material has decayed. So I wanted to make sure we had enough counts. So when I did that out, and it just seems like it's white hot, like it's going to melt through the table. It's not really. You can see how, and this is one of the things we're going to study the last experiment we're going to do, where we're going to show the radiation, or the counts per minute, as by distance from the sample. So you can see it's not as bad as it seemed, but it certainly was pretty astounding to see. You can see just pulling away slightly will really reduce the number of counts. Okay, this is the gamma radiation source, the cobalt-60. So gamma rays are high energy electromagnetic radiation, high energy photons. See lots of counts. All right, so this one I'm going to do pretty quickly, because you can see that if we put the aluminum foil in there, no effect. Probably a slight, if you were to take the counts over the course of a minute, you'd notice a slight difference. Here's the plastic, but nothing that you can really hear or see just looking at the monitor here. No noticeable effect from the plastic. Here's a thicker piece of aluminum. Nothing. And then here, this is the most astounding one. This is the lead. This white part is just the holder. But you can see the lead here. It's a 1/4 inch of lead. So listen to the counts. So it's right on there. No noticeable effect. I'm sure there is slightly, but that just shows that gamma particles can go through even a 1/4 inch of lead as if it's not there. So pretty impressive. So here are the nuclear equations for the production of the barium-137. So cesium-137 breaks down into barium-137, and that M means metastable, so that's going to go on to produce gamma particle. You can see that cesium has a half-life of 30 years. So the generator that we got about 10 years ago, so we got a lot of use left in it, left to go. And then you see the barium-137, the metastable form of it, has a half-life of under 3 minutes, and that's what we're going to determine what the half-life is. And you see it'll break up into stable barium-137, and we have our gamma particle that we will be counting. Okay, well, we want to get our barium-137 sample. So this is saline solution. Put this in to beaker. And then we're going to draw up some of the saline solution. Usually I have 8 of them that I have to make per class, but it's just this one here. Now, so it won't need very much. Okay, here's our isotope generator. Cesium barium-137 metastable. And then see, this indicates the flow of the saline solution. It's going to be put in, we're going to put the syringe here on top. It's going to push the saline solution through, and then out the other side will come the dissolved barium-137 in drops, and we're going to put 5 or 6 drops onto the watch glass, and then that's going to go under the radiation counter. Okay, so we got to take this off here, and this side off, and then put this here. Well, I can show it here. Okay, so, and then you don't want to go too quick, but you just put a little pressure behind it. And normally I wouldn't put this high, that high, but I want you to see the drops. Two, 3, 4, 5, 6. I'm going to put a lot of them in there just because it's going to take me a while to get to the next step. And the thing is that the half-life of the barium is less than 3 minutes. So in the time I do this, make sure everything's put away, it's going to take me probably 1 half-life to get this over to the radiation counter. Okay, you can hear it going, and I'm going to set it up, and I need the timer. So, turn that on, and what I'm going to do is reset it, and new, and start this. Okay, so I'm going to shut that sound off in a second, but when this gets to 60 seconds, I'm going to take the reading here. When it gets to 120 seconds, I'm going to take the next reading. I'm not going to keep zeroing it. I'm just going to let the counts increase, and we'll figure out how many counts there were per minute from each of the readings. So let me set this down. Okay. Just wanted to get... And you can see that it's going to be an estimate when we get to 60, but that's fine. It works out really well. If I'm off by 20 or 30 counts out of thousands, not a big deal. Okay, so we'll just do the first 2 minutes, and after this first minute, I'm shutting that sound off. It's getting to be annoying. Okay, so we got 54. So I'm going to say 2800, and that's going to be plenty close. Whoops. And, much better. Let's do that. Okay. And I'm just going to do out, I guess I'll do the second minute and the third minute, and then the rest of them I'll do off screen. So we're at a minute and a half, because I need to do about 19 minutes worth here so that we get a nice graph when we're done. So it's you're going to see that it's going to drop away as it should, but yeah, you don't want to watch every single second here. And that's the thing. This is set in seconds, so I got to think in terms of seconds. It's 120, then 180, then 240. Okay, here we go. So I'll say 5,000 for that one. Okay. And just so you can see that it is, so it was 2,800, then 5,000. So if it had stayed steady, it would have been 5,600, but you can see it's already dropping. So this number here, that's where it should have been, but it's slowing down like it should. And the half-life is under 3 minutes, so we should see a really noticeable drop each time. I'll do this last one, and then the rest of them will just be put in the data sheet at the end of the lab. So it's 3 minutes, so we want 180 seconds. And 7, 8. So we'll say 6650. And we'll stop here, and I'll keep going, but I'll put the data at the end of the lab. Okay, we're coming up on 20 minutes, 1,200 seconds. And you can see, I want you to hear the counts and see how slow they're getting. Trying to find a place to put this. So 1,200. And now I can write them down, right down to the count, 12. And you can hear that it's just above background radiation. And in a few more minutes, it'll be all of the barium 137 that was in a metastable state will have decayed. Okay, now we have the gamma source, the orange one here, and I'm using the other source to get the height. Whoops. And that's about 1 centimeter. It doesn't have to be absolutely perfect, but it looks good. Looks like the monitor is 1 centimeter from the gamma source. So move this over so we can see the counts. There we go. I think I broke it, but it's holding. Okay, good. So what we're going to do is going to reset it. No, it's gonna, there it is. And I've got the timer going here. And we're gonna have the counts for 1 minute, and then I'm going to raise this up 1 centimeter. So it's 2 centimeters away. Do the same thing, 3 centimeters, and so on. So I'm just gonna do this first one here so you can see what I'm doing, and then and then we'll see, we might do a second one on screen here. I think so. We'll do the 2 centimeter one, but that'll give you an idea of what we're up against here. You can see a lot of counts. I just don't know where this is so low. Just kind of go in there for a second. Okay, so we're at 44 seconds, 45, 46. See, we're getting to 52, 53, 54, 55, 56, 57, 58, 59. So 1963 is what I saw. And so that's at 1 centimeter. Okay, and I raised the monitor up another centimeter, so it's now 2 centimeters from the sample. And since I don't have to touch the sample or move it at all, I can just make this easier. So I'm going to reset the counter and then start the timer, and we'll let this go for a minute. And we're going to see, what we should see is that the number of counts drops away, because this radiation coming out of here isn't coming out and just straight up, even though it's, you know, that's what it looks like. It looks like everything's going to come out off of this surface. Well, it's going to go off in all the different directions that it can. So as we pull away, we should see fewer counts, because a lot of the right down really close, you should have this beam that's going almost directly in, but as we go further away, it's going to funnel outwards. And actually, it's going off in every possible direction. All right, so we are at, the further away we are, the fewer counts we should see. So this is 50, 3, 7, 8, 9. So I saw 914. All right, and then the other ones we'll have off. I'll list later at the end of the lab.